In this lecture, we will be talking about ion sources, which is the most important part of any accelerator. So this information will be useful to all types of accelerators. Now, point which I want to discuss is that since you have seen that in the case of tandem accelerator and the peloton accelerator, negative ions are injected. Therefore, you should know about what is negative ion and how they are generated. So proton accelerators use charge, which is plus. Electron accelerators use charge, which is minus. Heavy ions will depend on what is the charge state. Now, at this moment, I would like to point out that in the case of negative ion, the only singly negative ions have been obtained. It has been a lot of experiments have been done to see if doubly negative ions or multiple negative ions can be formed, and it has not been successful. Otherwise, suppose doubly negative ions are also formed, then it would be possible to accelerate ions to twice the energy in the first column itself. Therefore, you can get higher energies. But unfortunately, it has not been possible. And therefore, now positive ions, it is easy to remove. Suppose you take oxygen 16, which has 8 electrons. Remove all the 8 electrons, then it will be oxygen 8 plus. So Q becomes 8 times. So energy in the case of tandem or the peloton will be 1 plus 8 means 9 times of the voltage. Now, what is this negative ions? How you get this negative ions? You can see that atom, for example, we can get additional electron. Then, for example, if you take H, then it has only one electron, and that will go to 1s1. That's the orbital. And suppose you have He, helium, then in ground state, neutral, and it will be another electron will go into the s orbital, and it will become 1s2. And S can have only 2 electrons, so it will have this. While if you add 1 electron to hydrogen, then that extra electron can still sit in the s orbital, and it can easily accommodate one more, so it will be 1s2, which is a stable configuration. While in the case of He minus, if you try to add 1 electron, then 1s2 is full, so it will go to the next. Unfortunately, this He minus is not possible in ground state. However, there is a metastable state where the negative ion of helium is possible, and it is formed for a short period, for about 360 microsecond. In the case of, for example, oxygen, if it is a neutral atom, then the configuration will be 1s2, 2s2, and 2p4. It has 8 electrons. So P can have still 2 more electrons. Therefore, O minus is possible without any problem. So if an O minus if you take, then it will have 2 plus 5. Still 1 more electron, but unfortunately binding energy does not allow this to happen. So helium is an inert gas and has 2 electrons in the orbit. Configuration is this. H minus should be 1s2, 2s in ground state, but it is not found. Binding energy calculations show that. However, simulations as well as experiments have shown that there is a state is called 1s, 2s, 2p. That means this electrons, they get distributed to 1 in 1s, 2s, 2p, and that state is called 4p, 5 and half, metastable state which has a lifetime of 359 microsecond. So binding energy of 77 millielectronvolts. So it's very loosely bound. However, in the case of ground state, the binding energy is very, very small. So it is not possible to. So here I want to emphasize that the lifetime of this metastable state is about 359 microsecond, and that has been measured very accurately. And earlier by mistake I told by 70 microsecond. 70 microsecond is for some other state. Here for this metastable state it is 359 plus minus 0.7. So very accurate measurements have been done. However, this time microsecond is good enough to accelerate the point. So in the case of pelotons or even tandem, this helium is accelerated further. And first column section, the He minus will be accelerated. There in the terminal, in the stripper, it is possible to remove both the electrons, which was not possible in the case of Van de Graaff, and because of power limitation. Here it is possible, so you get 3 times energy rather than 2 times. So that's the advantage of peloton as well as tandem. Now this has tremendous amount of this negative ion formation thing in peloton has tremendous amount of advantages, because there are many atoms which do not form negative ions, and that gives tremendous amount of advantages. All the negative in ground state, all the inert gases do not form negative because their outermost orbits are completely full. So and if you want to form the negative ion, that extra electron which you are putting in has to go to a next orbital which is has a binding energy machine. So all inert gases do not form. None of the inert gases form negative ions. For example, inert gases are helium, neon, argon, xenon, krypton, so on. And in addition to these inert gases, another atom, nitrogen 14, also does not form negative ions. And this is a bonus for scientific communities, because this allows us to do a very accurate measurements as far as accelerator mass spectrometry is concerned, where we measure the, let's say for carbon 14 to carbon 12 ratio. And since nitrogen is not forming negative ions, so it does not interfere with the carbon 14 dating. And we are able to do good measurements on this. And not only that, since these inert gases don't form negative ions, so that is again an advantage for various kind of measurements, where carbon 14 negative and aluminum 26 or iron 55 or iodine 129, they are used in this because there is no interference from these isobars which are shown below, that nitrogen 14, magnesium 26, manganese 55 or xenon 129. So because there is no interference from isobars, that is why we are able to get much higher accuracy in the measurements. Carbon 14 formed in the upper atmosphere through the reaction between cosmic rays neutrons and nitrogen 14. So this is the reaction, and this carbon dioxide with carbon 14 is taken by the plants as long as they are alive, and so there will be a certain amount of carbon 14 there, and as soon as the plant dies, this intake of this carbon 14 stops. So by measuring the carbon 14 by carbon 12 ratios, you can easily find out what is the age of that plant or living being. Similarly, by measuring the ratio of iodine 129 to 127, you can also measure whether in that area any nuclear activity has taken place, whether it could be nuclear leakage in the reactor or some device testing has been done in that area. So by measuring this iodine 129, you can measure that. So this whole process where we measure this is called accelerator mass spectrometry, and these tandem and pelotons are used. In fact, these tandem and pelotons are known as ultra-sensitive mass spectrometers, and this is a field which is very widely used. And now dedicated peloton small energy accelerators, peloton accelerators are built. They are in thousands in number, which are used for AMS work, and very accurate measurements are possible. Accelerators nowadays, even 500 kV to 1 MV peloton accelerators are also built explicitly for AMS purposes, and they are very effectively used for this purpose. This is, as I said, that this is a very important component of, in fact, 80% of downtime in any accelerator is because of malfunctioning of ion source. Therefore, it has to be properly designed, built and tested before it is installed in the accelerator. Now, in earlier lectures, we have discussed different kind of ion sources, and in fact not only in basic research but also in the applied research these things are very important. For example, negative ion sources are very useful in the field of accelerator mass spectrometry, where the identification of various elements can be done with the almost 10⁻⁻15 sensitivity, and therefore these negative ions, some elements form negative ions, others don't form, and that is the characteristic of the property used in the case of tandem and peloton kind of accelerators, and sensitivity of detection of many elements in accelerator mass spectrometry depends on that. And since we have to inject negative ions in the case of tandem and peloton accelerators, therefore they are called ultra-sensitive mass spectrometers. Because now coming back to ion sources, different techniques are used for different ions, and this is the field, I think, which has been studied, and research R&D has been done to the maximum level on the ion sources. So there are very large number of ion sources have been built, and their performance has been improved considerably over the period of time. Now we talked about that there are main three kinds of ion sources. One is electrons, and they are not ions, they are electrons, and positive ions and negative ions. Positive ions are used in the Venn diagram or anywhere, including the Cockcroft-Walton, but negative ions are used in the case of tandems and peloton accelerators, and that is why these there is an advantage in using these. And this I have discussed earlier. Then there is another kind of ion source, which is called neutral beams. And these neutral beams are very useful, and they are required for system like tokamak. Recently, in the recent past, another kind of beams are required, and they are called PVAR, anti-protons or anti-particles. So these beams are available, for nuclear reaction studies or particle physics studies, and they are available at few places. For example, in Tabatron as at Fermilab, USA, 1 TeV anti-proton beam. Anti-proton is P bar. That means P bar. It is defined like this. So it is P bar. You can call it. These are the reactions or the interactions which people study, and that is available at Tabatron, where the 1 TeV by 1 TeV beams are studied, reaction. And there is another facility, and where again the anti-proton beams are available for this facility itself is called Facility for Anti-Proton and Ion Research. That is called FAIR at GSI, Germany, where these beams will be available. Now, coming to details of ion sources, the easiest one and most studied one is electron sources, and that is a very simple source, and there are two techniques which are used. One is thermionic emission. That means you have a filament. Here you can see filament, and if you pass the current, then it will get heated, temperature will go up, and the electrons will come out, and then you can focus them or you can guide them. Another way of doing is that you have a like a sharp point here, and apply a voltage. Then as the gradient is inversely proportional to the tip radius. So since it is almost like zero, so it will be very high. So field ionization will take place around this, and lot of electrons will be coming out. And of course, different kind of crystals and different kind of things are used for depending upon their properties. And then you can get lot of electrons. So electron beams even in amperes have been possible, and they have been achieved. So either by increasing the temperature of this or by field ionization, field emission, these electron beams are, and they are, as I said, that they are the most studied sources among all the others. And the reason being that electrons are used everywhere, whether it is medical or it is national security or food irradiation, and therefore they are studied well. Now let me just give an overview of ion sources, how they are produced and what kind of ion sources are available. Mainly, in addition to this electron beams, we have positive ion sources, as I mentioned. For example, in the case of Van de Graaff accelerator or Cockcroft-Walton, they are positive ions are used. We can also use negative ions there if the terminal is raised to the negative voltage. Or you can have peloton and tandem kind of things where negative ions are injected. So what are the various techniques and what kind of ion sources are very famous for these two things? See, for example, you can see a list of various types of ion sources. I am not going to discuss all of them, but I would like to discuss few of them which are most popular. For example, there is one called dioplasmatron, which can produce both positive as well as negative ions. See, you can see there that is listed at both the sides. So dioplasmatron is one which can give you both positive and negative ions. And then there is another very important ion source which is called Isnick's ion source, which is a must for any peloton accelerator, and it is a source of negative ions using cesium sputtering. And then there is another ion source which is called alpha-TROS, which is again a source of negative ions and particularly developed for peloton accelerators. And this is also pretty famous. There are many other kind of things. There are the target ion sources for radioactive ion sources production and things like that. So there are different techniques have been developed, and lot of R&D has been done to develop these kind of ion sources. For example, charge exchange also is another. In fact, this is alpha-TROS ion source also is nothing but this charge exchange type.